Going to end at 1 o'clock. I have a meeting, unfortunately. Okay, so today we're finally going to talk about the connection between on-shell diagrams and the positive Grassmannian that I've been promising for a while and not getting to. Remember that we understood last time what the invariant content of these reduced on-shell diagrams are, or sometimes called playback graphs. So if we had a picture like this, we saw that first, on general grounds, this permutation where we go into the graph and we make a right turn at a black vertex and a left turn at a white vertex, was an invariant under the merge, unmerge, and the square moves. And I also told you how to interpret that permutation as telling you something about the chain of consecutive linear dependencies between these vectors thought of as column vectors for a k by n matrix. Okay, so this permutation A to sigma of A has the significance that sigma of A, that column CA is contained in the span of CA plus 1 up to C sigma of A. Right? Okay. And I also told you how to read off the dimension of the configuration from drawing this picture of actually drawing the permutations and counting the number of dots in the diagram and so on. Okay. So so let's keep saying a few things about this before I tell you about positivity. Let's actually go back to this example, and in this example, if you remember, what this cell looks like. Again, I don't really know about positivity, so I shouldn't really be drawing it yet as a convex polygon, but I am, because that's what will end up being true. Okay, so in this configuration, 3, 4, 5 are on a line. And how do we see that 3, 4, 5 are on a line? Well, this permutation is telling us that. Okay, so it tells us, for example, that 3 is contained in the span of 4 plus 5. So that 3 to 5 is telling us that 3, 4, 5 is on a line. Okay, and so, so in this configuration, one of the minors, the minor 3, 4, 5, has gone to 0. Okay, good. Now remember, this was also one of our terms in BCFW, right? And we also saw that all the terms in BCFW are basically the same thing, just shifting the indices over. All right, so the first thing I want to do is tell you how we go from these pictures, which are pictures with lambdas and lambda tildes, to momentum twistor space. Okay? So this is just a little aside about how do we go from these on-shell diagrams. At least one way, how do we go from these on-shell diagrams, which are in lambda and lambda tilde space, to something in momentum twistor space? Next lecture, we'll do this sort of intrinsically directly in momentum twistor space, but here we started off with a picture of on-shell diagrams, amalgamation, all that stuff in lambda and lambda tilde, and I want to say how from this upstairs thing we can go downstairs to momentum twistor space. Well, if you remember, in our map, we had the following map. That we talked about this. And here I won't use k and k hat the way I did before. I'll change notation slightly. So here we have this kind of object that we've been talking about. And long ago, 2 weeks ago, we showed that thinking of this as an integral over k-planes in n dimensions, where the k-plane C has got to contain the plane lambda, that was a little redundant. If we just made it manifest that it contained the plane lambda and did a little bit of natural linear algebra, then this was actually exactly equal to delta 4 of momentum conservation, delta of Suzy over the Park-Taylor factor, and then multiplied by exactly the same kind of integral, except now k has gone down by 2. Okay, because I've gone from, and now I have a new matrix D, and now I have the minors, the k by 2 minors of this matrix. And exactly the same thing of D and the momentum twistor variables. Okay, and that was the connection. That's how we could see the objects we're talking about are both conformal and dual conformal invariant. Because from here, we saw conformal invariance very simply by going to a twistor space, and this makes the dual conformal symmetry manifest. But if you remember, what's the connection? What was the connection between the minors of C and the minors of D? Okay, the whole point was that we had this matrix C, the big matrix C. We put lambdas up here, okay, and then we did this change of variable so that the minors of C were equal to some factor times the minors of D. That was the whole point, right, of the transformation that took us from twistors to momentum twistors. So there's a 2 up here, there's a k minus 2 down here, and the relation was that the minors of C, and I'll write a little more symmetrically now. This was some factor that I think was like 1, 2, 2, 3, up to k minus 1k, times this smaller minor where you chop off C1 and CK, D2 up to dk minus 1. Okay, so that was the relationship between the two matrices. And so what do we learn now in our example? In our example, we had a 3 by 6 matrix where the minor 3, 4, 5 went to 0. Okay, so that means that the D matrix, so in our example, so we have a 3 by 5 matrix, C, a 3 by 6 matrix. Okay, so we're going to go from here to a matrix D, which is just 1 by 6. Okay, it has D1, D2, D3, D4, D5, D6. But what do we know if 3, 4, 5 is 0 here? What do we know on this side? So 3, 4, 5 is equal to 3, 4 times 4, 5 times D4. So we learn from here that D4 is 0. Okay? So this is an extremely simple matrix. It's a 1 by 6 matrix where D4 is equal to 0. Okay? So before doing anything else, let's first compute what this guy is, and we'll finally recognize an object that I've written down a number of times, but we could have also derived, very boneheadedly just by plugging and chugging, but now we see it a little more conceptually. So first, what is our object? So now I have an integral dd1 over d1, dd6 over d6, but there's no d4, right? d4 is missing. d4 is 0. So let me be very explicit about that. dd2 dd3, d4 is missing, so dd5 over d5, dd6 over d6. Delta 4/4, d1 z1 plus d6 z6, and again, d4 is missing. Okay, this integral, remember, is now mod GL1. The k is equal to 1 here, so it's mod GL1. And so let's do this integral once and for all. This is a very basic object in this story. It's called an R invariant. So let's define for any 5 labels, 1, 2, 3, 4, 5, what is the integral dd1 over d1 up to dd5 over d5, delta 4/4, d1 z1 plus d5 z5. Okay, once again, this integral is mod GL1. Okay, so what is this guy? Well, we can use the mod GL1, let's say, to set d5 to 1. Okay, so then very concretely, this is the integral dd1 over d1, dd4 over d4, and then I have a delta 4/4, d1 z1 plus d2 z2 plus z5. Okay? And now you see the point. There's no integral to do here, right? I have exactly as many delta functions as I have integration variables. So I'm going to just completely solve for d1, d2, d3, and d4 and shove in. Okay, so how do I solve for d1? How do I solve for the d's? Well, that's our favorite Pluker-Schouten-Kramer identity. Okay, so I solve this by saying negative z5 is d1 z1 plus d4 z4. And let me contract this equation, for example, with 2, 3, 4. If I contract it with 2, 3, 4, I get negative 5, 2, 3, 4 is equal to, and here I'm only going to get a single term, right? I'm going to get the term d1, 1, 2, 3, 4. And all the rest of them will vanish. Okay, so again, that's our favorite identity that tells us how to write a vector as a linear combination of 4 other vectors in this case. This is a 4 vector. So d1 is equal to d1 is equal to 2, 3, 4, 5 over 1, 2, 3, 4, and so on. So d2 will equal 1, 3, 4, 5 over 1, 2, 3, 4, etc. Okay. So what does this give us for the integral? So that integral is equal to, okay, first there's a Jacobian from solving for all these d's on the support of the delta function, right? What is a Jacobian? It's 1 over 1, 2, 3, 4. I'm solving for everyone in terms of 1, 2, 3, and 4. Okay, so there's a Jacobian 1 over 1, 2, 3, 4. This is a Jacobian from delta. Next, I have all the 1 over d's. So all the 1 over d's, like d1 is 2, 3, 4, 5 over 1, 2, 3, 4. The next one is 1, 3, 4, 5 over 1, 2, 3, 4. Okay, and finally, I have 5, 1, 2, 3 over 1, 2, 3, 4. And finally, I just have to shove in the delta function involving the etas, right? So the last thing in the eta is now eta 5 plus eta 1 is like 1, 2, is like 2, 3, 4, 5 over 1, 2, 3, 4. Eta 1 plus 1, 3, 4, 5 over 1, 2, 3, 4, eta 2 plus dot dot. Okay? So we're almost home free. First, let me rewrite the deltas to make it a little more symmetrical looking. I'm just going to put a 1, 2, 3, 4 here over 1, 2, 3, 4. And then I'm going to pull out an overall 1 over 1, 2, 3, 4 to the 4th. Okay? So if I do that, I will finally end up getting 1 over there's 4 1, 2, 3, 4s down here that cancel the 4 1, 2, 3, 4s there. But there's an overall 1 over 1, 2, 3, 4 from the Jacobian left. So I get all 5 factors downstairs beautifully. Okay, and upstairs we get delta 4, 1, 2, 3, 4, eta 5. Okay, which is the object that we've talked about before. Okay, but now we've seen, now we've come full circle, and now you see how all of this is done basically for free. Okay, we take BCFW, we take the 3 points, we glue them to get the 4 points, we glue them to get the higher point, all at the level of the permutation. Okay. So then from the permutation, we look at what the configuration looked like, we see what minor goes to 0, and we descend to momentum twistor space and immediately write down the answer. Okay? So, and this is much more transparent than you could do it. I think I put it on one of your problem sets. You could do it. You could take one of the BCFW terms and just slavishly plug in that the lambda tilde is written in terms of the z's and so on. And after some work, you would recognize all the 4 brackets emerging and everything. Okay? So of course you can do it that way as well. That's the way it was originally done. But this makes it more transparent. What is going on? Okay. But now let me say more general facts. So here we just saw how we get the answer. But more generally, if you have some BCFW term, anything, any object in momentum space, lambda and lambda tildes, any on-shell diagram that's associated with a permutation, it has to descend under the map that we've talked about to something in momentum twistor space. Okay? So now, so it's some kind of on-shell diagram in momentum twistor space. As I said, next time I'll tell you more about intrinsically what these on-shell diagrams are supposed to look like in momentum twistor space. They have a different interpretation than gluing together black and white amplitudes. Okay? But in any case, we should be able to go from some permutation with some k to some other permutation where the k is replaced by k minus 2. Okay? So what's your guess? What do you think? So in general, what do you think the map could possibly be that takes us from one thing to another? I somehow have to take you with a permutation that has a certain k to another permutation that k is down by 2. And remember the interpretation of k. K is a number that jump back, right? Or k of them go forward, if you insist on writing the permutation so that everyone goes forward. Any guesses before we do an example and then see what the formula is? What do you think the simplest way to lower the overall permutation by the overall k by 2 would be? No, that wouldn't do it, because you would. It should be some formula that works no matter what the initial permutation looks. Essentially, no matter what the initial permutation looks like. All right, let's see what's going on in this example. Remember, before we write the answer, recall that the sum over a of sigma of a minus a, this is counting the number that jump back. This is n times k. Okay, so this is the same as n times the number that jump back. Okay, but let's look at what the permutation looks like in this D space now. So to begin with, remember I had this in C. I had this permutation 1 to 4, 2 to 6 equals 4, 3 to 5, 4 to 1 equals 7, 5 to 2 equals 8, 6 to 3 equals 9. Now, what do we have in D? D, I just have this matrix, something, 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 0, something, something. 1, 2, 3, 4, 5, 6. So what is the permutation for D? All right, well, 1 goes to 2. 2 goes to 3. 3 goes to 5. Because 4 is 0. 4 goes to itself. 5 goes to 6. And 6 goes to 1 equals 7. OK? All right. So now I'm going to do something here. I'm going to take this permutation, and everybody I'm going to drop by 2. OK? I just subtract 2 from everyone. You see, that's guaranteed to lower k by 2. Right? That's the answer. You just drop the fucking permutation by 2. Okay, not quite, not quite. So we'll see. If I drop it by 2, I'll get 2. Here I'll get 6. This was 4 equals 6. Minus 2 equals 4. 5 minus 2 equals 3. 7 minus 2 equals 5. 8 minus 2 equals 6. 9 minus 2 equals 7. OK, you see that this is actually just shifted relative to this by 1. Right? So in fact, the general rule, and that has something to do with our convention for what we call the D matrix. We made the D matrix sort of symmetrical with respect to stripping off one column on the right and the left in reducing k by 1. Okay? So in fact, here is the general rule. The general rule is that the sigma in D space for A is equal to the sigma in C space for A minus 1 minus 1. OK? So what you have to do is go, in order to see where does 3 go, right? So 3 goes to 5, but that 3, I go here, 3. I have to see where 2 goes. Okay, so 2 would go to 4, and I subtract 1. Okay? Okay. Yes? Sorry? Oh, I'm sorry. This was not, I did that wrong. I'm sorry. Just 2 goes, sorry, 2 went to 6. I apologize. Okay, 2 went to 6, minus 2 is equal to 4. OK, so that's the connection between the C and the D spaces at the level of the permutation. Shall we do it again? So sigma of 3.
We did on the left with C would be if sigma of D of A is sigma C of A minus 2, but that's not the formula you wrote.
Sorry?
You wrote the formula sigma D of A is sigma C of A minus 1 then minus 2.
Oh, sorry. Yeah, sorry. So here I just wanted to show, yeah. So let's, here I just wanted, so if I take this permutation and I just shift everyone up by 1, I get the permutation that I want. This is the correct formula. So if I ask, yes. So if I ask, so let's forget this minus 2 now. I was just illustrating that we're dropping the k by 1, and it looks like the same permutation. But if I ask where does 3 go, so 3 is supposed to go to 5. But 3, I have to look at where 2 goes. 2 goes to 4, and I have to subtract 1.
2 goes to 6.
Oh, sorry, 2 goes to 6? I have to 2 goes to 6, and so let me subtract 1 from here. Good. Okay, so 3, I have to go to see where does 2 goes to 6, subtract 1 goes to 5. 5, 4 goes to 7, subtract 1 goes to 6. Okay.
Take the table and you add 1 to the left side and subtract 1 to the right side? If you want to just draw the table.
Yeah, if you wanted to, yeah. So if you, yes, that's right. essentially it's dropping everything by 2 up to a cyclic rotation. Okay, so the point is that dropping everything by 2 is the important part. That's the thing, which is dropping k by 2. And you can actually prove that, I'm just showing you in this example, but it's very, very simple to prove from the relationship we saw between the C and the D matrices that this is what's going on. Notice one small point. The C permutation is always well-defined, but for this thing to be always well-defined, it had better be that in the C permutation, I'm always jumping by more than 2, so that when I subtract 2, it doesn't, I still get a legal permutation. That's actually very beautifully reflected in our answer. Because remember, our C matrix has got to have the lambdas on the top. And in the entire derivation, we're assuming that the lambda matrix is generic. None of the minors of the lambda matrix vanish. If any of the minors of the lambda matrix vanished, our map to momentum twistor space would become singular, because we have that Park-Taylor factor sitting out in front. So we must assume that the lambdas are generic. And assuming the lambdas are generic precisely guarantees that you always jump up by more than 2. Okay, so that when you subtract by 2 from everyone, you still have a legal affine permutation where everyone is moving to the right. Okay? All right. Okay, so now let's finally talk about positivity. And we've already seen lots of sort of intuition for it. We've seen that the boundary structure for example, we just saw that the cell that we got, which was not a top cell, it had 8 variables, not 9 variables. And all of these cells look the same, but they all look like they involve consecutive 3, 4, 5 becoming collinear and so on, which is exactly what we expected based on positivity. And there are many ways of talking about why positivity is really natural here. And you could explore many more of them on your own. But let me give you at least sort of one quick way of seeing why these things are related to each other, which has to do with the way that we're building up our cells. Remember, we're building up our cells by bridging. Okay? And the bridging operation naturally preserves positivity, if you have positivity. So what do I mean by that? You see, we're bridging by neighbors. So let's first not worry about subtleties, about jumping over columns and so on. We're bridging over when I do an A plus 1 bridge, what I'm doing is I'm taking column CA plus 1 and I'm making a new column CA plus 1 hat, which is CA plus 1 plus some Z times CA. And therefore, let's say that it was the case that somehow you had some minor involving, let's say we had some minor involving A plus 1. So on the left and the right, we have anything. A plus 1 is anything there. This is going to go, so this is CA plus 1. This is going to go to the same thing with some C hat A plus 1, which is equal to CA plus 1, whatever we had before, plus Z times the same thing with A plus 1 replaced by A. And so you see that if things were ordered such that this was ordered, this will also be ordered. And so if you started off in a configuration where the minors were positive, this operation will preserve positivity so long as these variables Z are positive. Okay, so this will preserve positivity Okay? And obviously, we begin with a configuration where everything is 0 except one minor, which is 1. So we start with something trivially positive. But then as we build everything up, so long as we make the bridge variables positive, where it's just guaranteed that we're going to build bigger and bigger matrices, all of whose minors are positive. Okay, so this is one way in which we can see that this entire story is about building large positive matrices by starting with simple ones and gradually gluing in Now, here I'm describing in the language of bridging. You can even describe it at the very beginning in the language of amalgamation to begin with. In other words, really plonking down a bunch of G13s and G23s and talking about the operations that we did in one fell swoop, where we just integrated over every one and we wrote down the boundary measurements. You can actually say that more gradually by saying, if you take two things and you glue two of them together, that preserves positivity, so long as the variables are appropriately positive. And then if you take two of them, two adjacent ones, and you glue them together, that preserves positivity. And so all we're doing is taking those positivity preserving operations and just doing them over and over and over again. Okay, so that's both. These are two related, not identical, but related ways of understanding that we're making something complicated out of a lot of simple building blocks that preserve positivity. So let's just see an example of how this works, and then I'll tell you there's only sort of one small subtlety, but let's do an example in G24. So positive G24. So let's say that we start off with this matrix. Okay? And so the associated permutation is 1 to 5, 2 to 6, 3 to 3, and 4 to 4. Right? So that should be clear. 1 just goes to itself. 5, 2 goes to itself. 6, 3 to 3, 4 to 4. Okay, so where can I bridge? Remember, when I go up, I have to bridge in a spot with the first consecutive place where I have a plus 1, but sigma of a should be larger than sigma of a plus 1. So in this case, I will start like bridging 2, 3, right? Because 6 is bigger than 3. So if I bridge 2, 3, that means that I shift C3 by something proportional to C2. Okay, so now we get a new matrix, 1, 0, 0, 1. And so this is going to be 0. Let's call it Z1. Okay? So now my permutation is 1 to 5, 2 to 3, which is proportional to 3, 3 to 6, and 4 to 4. Okay. So now what's the next one that I can do? Now I can do like 1, 2. I could also do a 3, 4, but let's do 1, 1, 1, 1, 2. Okay. So now I get 1, 0, Z2, 1, 0, Z1, 0, 0. Sorry, I forgot I'm Canadian today. Z2. Okay. Okay, so let's do the next one. Who's the next one we can do? We can do 3, 4. Right? So let's do 3, 4. So I have 1, 0, Z1. And so 4, I'm going to shift proportional to 3. So it's going to be 0, Z, Z3, Z1. Okay, and finally, I can do, and so now I have 1 to 3, 2 to 5, 3 to 4, 4 to 6. By the way, I mean, you don't, when you're doing this in practice, first, there's a package that does it for you in practice. Secondly, you don't actually have to slavishly write out the permutations. You sort of get used to just shifting the columns in the only way you can that increases the dimension. Okay, so for example, when I go back here, Why didn't I do 3, 4? Well, that's moronic, right? That's not going to buy me anything, okay? Why didn't I do 1, 2? Same reason, right? It doesn't actually increase the dimensionality of the configuration at all. 1 and 2 are independent vectors. After I added some variable, they're still independent vectors. I didn't increase the dimensionality of the configuration. So in practice, you don't have to sit there and slavishly write down these permutations. It's just if you do it, you'll never get it wrong, okay? In practice, you just shift columns by adjacent columns in the only way you can to increase the dimension of the configuration. And if you make the shift variables positive, you'll keep everything positive. So if we do the last step here, if I do 2, 3, then I get 1, 0, Z2, 1. And now this is the Z1 plus Z4, Z2, Z4, 0, Z3, Z1. So this is my final matrix. Okay? Oops. Z1. Yes, that's right. This is my final matrix. And so you see it has some sort of clever, parameterization of the entry so that all the minors are positive. 1, 2 is positive. Sorry, what have I done here? That should be. Oh, yeah, sorry. Yeah, everything's fine. Sorry. Yeah. So 1, 2 is positive. 1, everyone is positive. But now look at this one. This is Z2, Z1 plus Z2, Z4 minus Z2, Z4. Good. So it's Z2, Z1. Positive. Everyone is guaranteed to be positive so long as all the Zs are positive. OK. Now, there's only one minor subtlety. So this is positive in the G plus 2, 4 sense if all the Z1 to Z4 are positive. OK, so the minor subtlety we can see already in this example. So let's say we have this G23 example. Okay, so in this example, we have 1 goes to 4, 2 goes to 5, and 3 goes to 3. And so here, I want to bridge 1, 3, right? So I want to bridge 1, 3. So this is an example where I'm skipping over a column which is identified with itself plus n, right? So I'm skipping over column 2, which is identified to itself plus n. So these guys are not adjacent. 1 and 3 are not adjacent. And you can see that when I do this shift, C3 goes to C3 plus alpha C1, what is happening to the minor what's happening to the minor 2, 3 is going to, it was 0 to begin with, but 2, 3 goes to 2, 3 plus alpha 2, 1. And so, so this is just alpha, this is negative alpha. OK? So the only minor subtlety is that when I do bridging, to preserve positivity, in bridging, I have to send CA plus 1 goes to CA plus 1 plus negative 1 to the Q ZCA, where Q equals the number of B's between A and A plus 1 with sigma of B equals B plus N. Okay, so it just says that you have to pick up a minus sign when you bridge. when you jump over an odd number of self-identified columns like that. Okay, and that's it. So now, it's really, there are some quite non-trivial facts here that I'm not going to prove that this, in fact, is everything there is to the positive Rachmanian. Okay? That all the boundaries of the positive Rachmanian are described in this way. So that's quite non-trivial. But anyway, it all ends up. But from this point of view, I hope it's quite intuitive, and you see how to actually use it. Okay? So let's just give a brief summary then. So a summary is that we can start off life defining this space, the positive Rachmanian, the space of k-biand matrices where all the minors CA1 through CAK are greater than or equal to 0 when they're ordered. Okay? Okay. And the claim is that all the boundaries of the positive Rachmanian are associated with all boundaries of all dimension of GKN are associated with playback graphs, these unshelled diagrams, reduced unshelled diagrams / playback graphs. And that the invariant content is an affine permutation A to sigma of A with K jump back being what the meaning of K is. The decomposition of sigma into adjacent transpositions, the best we can do, the analog of adjacent transpositions, is completely the same as building on-shell diagrams / playback graphs from BCFW bridges and that when appropriately defined, when the bridge variables Z are positive, the matrix we construct, the point we construct, we cover a cell of G plus Ki. Okay. So to finish talking about this geometry, I now need to tell you, if you have a given cell, so a given on-shell diagram, a given cell of the positive Rachmanian, how do I find its boundaries? Okay, I want to find what the sort of lower dimensional boundaries are that are contained in that cell. Okay, and first, what do you think it is intuitively? Let's just think sort of very intuitively for a second, and then I'll give you a more formal definition. So let's go back to our favorite G24 example. So that picture was like a top cell. Right? This picture was a top cell. And we know that if I'm going to a boundary, there's fewer degrees of freedom. So how can I get fewer degrees of freedom from this picture? I can erase an edge. Okay? So if I take this picture and I erase an edge, let's say I erase that edge, then, Okay, from our usual trivial rules, I go down to something that looks like that. And that indeed does give you a one lower dimensional boundary of the Grassmannian, of G24 in this case. And I could have erased 4 edges, and they would have all been good. They would have all gone down one in dimension. Okay, now you might start getting nervous. What does it mean erasing edges when it starts getting very singular here and so on? But that's the basic idea, is that we want to learn how to erase edges. Okay, but in fact, it's very beautiful and natural what this operation is, thinking in terms of the affine permutation itself. Okay, so let me try to explain it. So if you remember, we drew this picture where I draw sort of 1, 2, 3, etc. Right? And 1, 2, and so on. And we had this picture like 1 goes somewhere, 3 goes somewhere, 2 goes somewhere, and so on. Okay. So, and if you also remember, the dimension of the configuration was the number of these intersection points. I had to count the number of these, let's say, vertical intersection points, and the dimensionality of the configuration was just a sort of number of these. So what we somehow need to do, if we want to drop the dimension by 1, right, is we somehow have to take one of these pictures and make a new picture where all I've done is delete 1 dot. Okay, so how do I do that? Well, I can do that as follows. If I have an A that goes into sigma of A, and I have a B that goes to sigma of B, and it looks like this, okay? So if my affine permutation has something that looks like this, then one of its boundary components, and then I'll do this in every way that I can from the graph. So one boundary is where I just interchange these guys. So A will go to sigma of B, B will go to sigma of A. Now, if you think about how we're building these things up by bridging, we're just undoing the bridge, right? Because after all, what we're doing with adjacent transpositions on the way up, so then we're just going to do it on the way down. But if you remember, we have this rule for how we have to bridge on the way up that we have to respect on the way down as well. Okay, so if I do this, one boundary will look like this. Now with A goes to sigma of B, and B goes to sigma of A. So you see, this is very nice because I lose precisely one intersection point. Okay, so I used to have an intersection point there, and I don't have an intersection point there anymore. Provided, however, that there is no crappy guy C between A and B. See, if there's anyone else in here, then I can't do it. If there's anyone else in there, then I'm losing too many dots. Okay? So I have to have that. So I have to have this in the language of this diagram. I have to have an A to sigma of A, a B to sigma of B, such that there's no C in between A and B, which goes in between, which is mapped under the permutation between sigma of A and sigma of B. If I say this in the language of the graphs, it's very natural. In the language of the graphs, this is what we're saying. So let's say I have, here's my graph, and I want to see whether there's some edge on the inside I can erase or not, right? I want to see whether there's an edge I can erase. So let's say here's some edge, and I want to see whether this edge is erasable or not. So maybe, who knows where these are going out somewhere. But I need to have the, I want to find an A and a B. And so A is going to have its permutation. So A is going to have its permutation doing its left-right path, whatever it does. But A is going to come through here and go out there and go to wherever A is going to end up. sigma of A. And B is going to do its own thing. I'm going to come in here and go out to some sigma of B. There is at most one edge. There may be no edges on which the permutations between A and B overlap. But there's, of course, at most one edge on which the permutation from A to sigma of A and B to sigma of B could overlap with each other. If the original graph is the reduced. And so you can make you can erase this edge if and only if there are no C's. So in this region 1 up here, there should be no C's that map under the permutation to something in region 2 in there. Okay, so in other words, everyone else should either stick within here, permute within here, or permute within there. And if you do that, what is the new boundary? Then I can erase this edge. If I do that, then I can erase this edge. Again, if there are no C's, if no C in region 1 goes to sigma C in region 2. All right, and if that happens, then I can erase this edge. And now A merrily will go to sigma of B, and B will go to sigma of A. And I haven't trapped anyone in between. Okay. All right, so let's just do a quick example to see how these boundaries work.
So
Yeah.
This sounds very much like 1PI.
Sorry?
This setup has a 1PI kind of feeling to it.
No, it's more than one PI. I mean, it's because, yeah, I mean, because it's not in one PI. It's something purely about the connectivity of the graph. This is about the connectivity of the left-right paths through the graph. Okay, so if you draw a given graph, there's all sorts of left-right paths through the graph, and then you're saying indeed that you want a left. You can erase an edge such that, as far as the left-right paths are concerned, if you delete the edge, it breaks the graph up into 2 distinct pieces. So in that sense, it's like 1PI, but you don't read it off from the graph. You read it off from the left-right paths through the graph. Okay. All right. So, so finally, let's give some an example of boundary structure. So let's again just do G24. So to begin with, we have let me just keep going a little bit here. Again, ultimately, we only care about what the picture looks like in one block between 1 and 4, but just to draw them all. So here's our permutation: 1 to 3, 2 to 4, 3 to 1, 4 to 2. Right? That's the basic top cell configuration, and also I have 4 to 2, 3 to 1, and so on. Okay, so this is what corresponds to a configuration of vectors that just looks like a bunch of generic vectors. So now, what is one of the boundaries that we can take? I can take, let's say, I had 1 to 3, 2 to 4. There's nothing in between these guys, so I can just going to interchange. 1 goes to 4, 2 goes to 3. Okay? So in here, I'm just changing things. So now I have a new boundary. Let's just draw it like this: 1 to 4 and 2 to 3. So I lost 1 degree of freedom there. Okay, so what does that correspond to? What does that boundary correspond to? Well, what do you think this looks like? So 2 goes to 3, so that means 2 is parallel to 3. So this boundary looks like 1, and then 2 and 3 parallel to each other, and then 4, generic. Okay. Okay. Now let's take another boundary. So what's a boundary of this boundary? Okay. A boundary of this boundary, for example, I could do like up here. So I had 3 to 1, 4 to 2, okay? And I could interchange them. Okay, so I have okay, so what does that look like? So I haven't changed the fact that 2 is parallel to 3, but 4 goes to 1 means that 4 is parallel to 1, right? So this boundary now looks like that. Or if I go back, let's see if I can undo all of this. If I go back to 3 goes to 1 and 4 goes to 2, now I can do something else just so you see what the more singular configurations look like. Like here I had 4 goes to 2. Let's see, what do I want to do? Yeah, I had 3 goes to 1, 4 goes to 2. Okay? So, no, let me, I think I want to do this one. Yeah. I want to do this one. I have 4 to 2 and 2 to 3. Okay. So now I'm going to do 4 to 3 and 2 back to itself, nothing. All right. So that one would look like this. So this is one of the, that's why I wanted to do this, just so you see what one of the slightly more singular ones looks like. So 4 is now going to go to 3. And just 2 goes to itself. So 2 is gone. Right? So just 2 goes to itself. So this also dropped the configuration in dimension by 1. Okay? The guy that I lost is this guy, okay? Which I used to count before, which I don't have anymore. And so what does this configuration look like? This configuration just looks like 2 is gone. Okay? 2 is gone to 0. And indeed, I have 4 goes to 3. Right? All these guys are independent. So 4 goes to 3, 3 goes to 1, and 1 goes to 4. Exactly as you would expect from this picture. Okay, so that's everything about the boundary structure of the positive Riemannian. So let me let me just say a couple of more words, and then I'll go in about 5 minutes. Sorry. So some more comments. First of all, I've described for you a way to associate a form with any cell. A form with any cell of the gamma of the positive Riemannian can just be the product of all the dzi over zi, a form of some cell of dimension d, product of I equals 1 to d, dzi over zi, for any way of representing that cell by bridging. It's a non-trivial claim that this form is the same, no matter how you bridge. No matter what coordinates you use, no matter how you build it up, that the form will always be the same. Okay? A given cell, remember, a given cell is not uniquely associated with a diagram. There are lots of different Playbit graphs, on-shell diagrams that represent the same cell. There are even lots of different ways of building up that Playbit graph or on-shell diagram by bridging. Okay? All of them will have their own variables, but the form that we build in the end is completely invariant. Okay? The form is the same. In particular, for the top cell there are zillions of ways of writing this as product from I equals 1 to k times n minus k, dzi over zi. But this form is nothing other than that form whose poles are the cyclic minors that we've talked about. Okay? And this is not a totally trivial fact, okay? But that this form that we can represent using positive coordinates is exactly, in any way of representing it, is the same as this one, which is a sort of coordinate-independent way of talking about what the object is. Furthermore, if you want to go from this top form down to the form on any lower cell, you just take residues. Okay, and that fact is obvious in this presentation. I have a stack of dz over z's, and all I have to do is set a bunch of z's to 0, take residues until I get down to any lower form that I like. Okay, so I can think of omega for any gamma as also some residue of omega top in any way that I like. So that's the sense in which we can think of our big integral. I can write that formal large integral down with this whole integration over the top form. And to get to any given on-shell diagram, I'm just taking residues to localize the integral to one of the facets of the positive Grassmannian. OK? OK, actually, there's a few more things to say about this. But since I have to go, let me not say it in a rushed way, and we'll begin next time by saying a few more things. And then next time, I will also talk about the interpretation of on-shell diagrams and BCFW, both at tree level and to all loop order, directly in momentum twister space. Okay, so by the end of next time, we'll be completely done with the on-shell diagrammatics and the construction of amplitudes in terms of on-shell processes, and we'll set up the question of what it is that tells us. So from here, you should get the idea that every cell of the positive Grassmannian. So just a quick summary. Physically, we think it's interesting to glue together black and white vertices corresponding to the basic 3-particle amplitudes on shell to build a collection of interesting objects. There are many fewer of these independent objects than you might naively think. They satisfy lots of intricate identities between each other. I haven't told you where the identities come from in a second. We'll start with that next time. But it shouldn't surprise you. The identities are homological statements. Okay? The identities are, you go to a one higher dimensional cell in the Grassmannian, and you add up everything you see on its boundaries. And adding up everything you see on this boundaries gives you 0. So that's the origin of all the identities. Okay, but anyway, you have this large collection of interesting objects that you can build the amplitude in terms of if you pick and choose in a particular way to glue them together. What tells you to pick and choose to glue them in a particular way is ultimately quantum field theory, because we can derive the recursion relations from factorization and the magical fact that the amplitude vanishes at infinity. It was a little bit of magic, but anyway, we could be instructed for how to glue these things together by the desire to make an answer that's local and unitary. On the other hand, we also see that these objects are spat out, are the answer to another question. Just what are the, we generalize the notion of a simplex into the Grassmannian, and we find that it has a much, much richer boundary structure than a simplex does. And in fact, all the boundaries of the positive Grassmannian are captured by exactly the same kind of pictures that we otherwise interpreted as on-shell scattering processes. Okay? So that fact is quite non-trivial, and you see that what sits underneath the entire thing is just this simple pictorial representation of affine permutations. Okay, so we go from the pictorial representation of affine permutations, it builds some subspace in the Grassmannian, which in turn computes some on-shell scattering process. But also from this point of view, so this is perfectly nice mathematically, but then we're saying something more. We're saying that some of these cells are privileged. We like some of them, and we like collections of some of them. Give me these guys. Or you can give it to me in lots of different ways, right? All these different ways of running the BCFW recursion relations give me lots of different collection of these guys. But why? What's nice about this collection of objects? So that's the question that we're going to get to next week. And that's the entire story of the amplitahedron, both at tree level and at loop level, is is going to tell us what's special about this collection of objects and what mathematical question they're answering. And the answer, as we've foreshadowed a number of times in the course, is that the different terms in BCFW are like little Lego blocks that are actually filling in and triangulating the amplitahedron. But it has some, it has some intrinsic definition, just generalizing the notion of polytopes into the Grassmannian. It has a simple intrinsic definition all on its own. And when we see that definition, we'll even learn other ways of getting the answer that don't look like BCFW or don't look like anything else, that involve different ways of triangulating this basic object. OK? All right. Sorry I had to leave early today, but I'll see you guys next time.